Mr. Tarot, in this calculus lesson we are going to be doing a lot of review, which will be nice. And we're actually learning a lot of everything we're learning in calculus so far is review. Like we first started talking about derivatives and really just went all the way back to Algebra 1 and started with finding slope. So we're going to be reviewing inverse functions with you. We're going to be using the definition of the inverse function to validate that two functions are inverses of themselves. Now I keep saying functions, so we will be talking about domain and range and possibly needing to restrict the domain of these functions so that they are inverse functions, not inverse relations. We are going to be, I'm going to give you a somewhat advanced question, and we're going to work through finding the inverse of this given function. And then we're ultimately going to get into, with that calculus, finding the derivative of inverse functions and walk through two examples. The first one kind of showing you how the formula works, and it'll be overly detailed, and then one last example to finish up the video. So, the inverse functions. Well, we know that, or hopefully remember that if we were given a function and asked to find its inverse, as we're going to do in our first big example, is we take the x and y values, we switch places, and we resolve for y. So we have just a linear function, y equals 2x plus 4, and just pretending like, I don't know how to graph a line with just a y-intercept and a slope, I've gotten a table of values, and there's a reason for that, where I've picked the values of -1, 0, 1, and 2, and found our y values, and plotted my function. It's right here in white. We have a y-intercept of 4 and a slope of 2, and I've picked out one particular point of 1, 6. Then I've taken my x and y variables, I've swapped places, and then I've resolved the second equation for y. So subtracting both sides by 4 and dividing by 2, we get y with an exponent of -1, which, when we're talking about inverse functions, doesn't mean write 1 over y. It's a inverse function. It works basically kind of like in the reverse order. With trig functions, you put an angle in, you get out the sides of a triangle. Well, the inverse function is you put in the sides of the triangle and you get out this angle measure. So the inverse of y, with the y being the original function 2x plus 4, is 1/2 x minus 2. And again, I've done a table of values. My x has a multiplication of 1/2, so I'm for convenient purposes with my table using even values. So 2, 4, and 6, and getting the y values of -1, 0, and 1. And then we have this, if you can see the color of this green line right here, which is the inverse. Now a couple of things I want to point out here, just in case you forgot it from algebra, is if you look at my table of values, I have -1, 2, where with the inverse function I have 2, -1. I have the original point of 0, 4 changing to a point of 4, 0. And then finally 1, 6 is of course being 6, 1. So not only are we seeing that we take the x and y variables and we switch places, but it happens with the actual coordinates of the t-tables. So what was the domain of my original function is becoming the range of my inverse function. And then graphically how that looks is we have this line of y equals x, and it kind of makes sense because we're taking those x and y values and switching places, that there's a reflection on this line where y and x are equal. And again, that's allowing the domain of the original function becoming the range of the inverse function, and you get this reflection over that line of y equals x. That's the graphical way of identifying inverse functions. So, in summary, reflections over the inverses are reflections over the line y equals x. We notice that the domain and range values switch places, and we want to point this out. This is what we're going to focus on actually at the end of the video, and we can see it just here in these simple linear functions. The derivative, which of course is at least the first derivative, right, is the slope of the original function. So the derivative of function f at CD is the reciprocal of the derivative of the inverse function at DC, switching again those domain and those range values. Now, these are linear functions, so the slope of these functions is going to remain constant. So I'm pointing out this 1, 6 and the 6, 1 because I know where the end of the video is going. Indeed, as you look at these two linear functions, we can see that the slope of the original function is 2, excuse me, and the slope of the inverse function is 1/2. Those are reciprocals. And for these two linear functions, the slopes are the reciprocals everywhere in the domain, but of course with calculus that's allowed us in the first derivative to find the slope of curves at a given point. So I'm just saying that if you're at a point in one function and you take the domain and range and swap them to find the point on the inverse function, that the slopes are going to be reciprocals of themselves. And again, that becomes a big deal in our last two examples. The definition of inverse functions. Well, a function g is the inverse of function f if f of g of x, so you do that composition of functions, is equal to x at when you're done simplifying, and that g of f of x is equal to, again, x. So you set up this composition and simplify, and in both, it has to be in both times f of g of x and g of f of x, they come out to be equal to x for each x in the domain of g and for each x in the domain of f. Just for clarity purposes, if you needed it, I went ahead and rewrote that expression as f of the inverse of f of x. So that inverse function is getting put into the original function, simplifies to x. And then the original function getting put into the inverse function also, not or, has to simplify to be x. So our first example is going to be just doing, using the definition of inverse functions to test whether two given functions are inverses. And we're going to do that right now. Show that functions f and g are inverse functions both analytically and graphically. Now, I just erased part of my example there, which I'll put back up in a second. And the reason I want to do that is I want to actually start the problem graphically, and again emphasize this restricting, sometimes needing to restrict domains of these functions so that they are inverse functions and not just relations. So we're going to focus on function g here first for just a moment, even though I kind of listed that as a second function. But function g is, got one squared term and it's x. So it's a parabola opening with that positive coefficient up. So this vertical parabola has a vertical stretch of 4 and it has a shift down of 1. So I know my vertex is going to be at 0, -1. Then with the vertical stretch, either I can talk about transformations, which I just hinted to, or let's just plug in a value like 1. 1 squared is 1, 4 times 1 is 1, and then 4 minus 1 is equal to 3. So we have a point of 1, 3. And then this, being a basic polynomial with the x having an even power, is going to pass the test for being an even function, which means it's symmetric to the y-axis, meaning that I can if I plug in opposite values, x and -x, I get the same y value. So, or I could just plug in -1, -1 squared is 1, times 4 is 4, minus 1 is again 3. So yes, indeed, there is some vertical symmetry, or at least symmetry to the y-axis, and the parabola is going to look something like this. And, a parabola is a function, but are these, I want to verify that these are inverse functions, that they're inverse functions to themselves. So if I take just my graph right now and I reflect it over the line y equals x, instead of going along the y-axis, it's going to run along the x-axis, and it would fail the vertical line test. So while my g of x is a function, f of x, if it were its inverse, it would be an inverse relation, and we want to restrict these to be inverse functions. So that part that I erased on my problem said that for my parabola that the x had to be greater than or equal to 0, and that is because, not because of any issues with graphing the parabola, but to force these to actually be inverse functions, not inverse relations. So there we go, there's g of x. Understanding that the domain of one function becomes the range of the other, I could actually just write these 2 points down, or even maybe a third, and just swap the x and y coordinates and sketch my inverse function or f of x immediately. But to talk about transformations for a second, f of x is equal to 1/2. I can pull that 1/2 out front and get the square root of x plus 1. So now this function has a vertical compression of a magnitude of 1/2, and this plus 1, now this plus 1 is inside the math function, not at the tail end, a constant basically kind of like all by itself. So that is going to be a shift to the left with a compression of 1/2. So my my function or my graph of f of x is going to look something like this. And we can see, I'll just have to talk over the air conditioner for a second before I can turn that off, that f of x and g of x, as much as I could, as good as I can draw this on a chalkboard, are showing as their reflections over this line again of y equals x. So that's our graphical sort of validation or verification that these are inverse functions. Now, graphs are just that. They can be graphs. They're approximations. Maybe with the tables and our calculators we can verify it more exactly, but let's do this analytically, which is a bit more reliable. So I'm going to check the first half of this check, and you're going to do the second half. We're going to do, or you could pause the video and do it both on your own. We have f of g of x, and we're going to validate that that is actually equal to just simply x. So we're going to take function g and put it into function x. So we have the square root of something plus 1 over 2. And that something that we're plugging in for x is g. So it's going to be 4x squared minus 1. Okay, so now we have the composition set up. There's nothing in front of these parentheses, no exponent, no denominator. There's a denominator of 2, but I'm talking about within the grouping symbol of the square root symbol. So this negative 1 and this positive 1 are just going to simply cancel out. We have the square root, a broken piece of chalk, of 4x squared, the square root of 4x squared over 2. The 4 is a perfect square, the x squared is a perfect square, and this is just simply one term. So we can square root, the term. The square root of 4 is 2. The square root of x squared is equal to x, and then over 2, and that simplifies to x. So that's the first half of the check. Now we need to go through as well and validate that, does g of f of x, does that equal x? So now you're going to set that up on your own. One thing, by the way, when you take an even power of a value that is also raised to that same even power, you're supposed to need to wrap that in absolute value symbols. So, this could possibly look like 2 divided by 2 is just 1 and just have a final answer of absolute value of x. But we have a restriction where x must be positive anyway, so there's no need to write those absolute value symbols. We're just assuming that it is positive as we do the problem. I'm going to review the answer, but just run through it, make sure you can do it yourself. All right, checks out both ways. G of f of x, f of g of x, they both come out to be x, so these are inverse functions. Let's go on to talking about the existence of inverse functions, put into words what I've said verbally, show you the steps of finding an inverse function, and do one example of, here's a function, find its inverse. We'll take it a little bit further than we did in maybe Algebra 2 or Pre-Calculus and involve a little bit of practice with derivatives to check for that one-to-one nature that we need to have an inverse function. The existence of an inverse function, well, a function has to have, for a function to have an inverse function, it must be one-to-one. Now, it has to first be a function, that's why I keep saying, function. But a one-to-one function, hopefully you remember, and if not, let's review it. That means, of course, that this, this function here that's increasing as we go to the right would pass the vertical line test. So no matter where I put a vertical line, it would only cross once, indicating that it's a function. And then the one-to-one part means that it would also pass the horizontal line test, where that I could not, or everywhere I could draw a horizontal line, it would only cross once. So that's one-to-one, at least as far as the graphical check, which is what you would have done in algebra or geometry. Now, we're into calculus, right? So we're going to be doing this. If, we need to know how to use our graphing calculators as well. So a visual inspection for a one-to-one check could certainly be sufficient. But we can check this with derivatives as well. Excuse me. If f is strictly monotonic, that means basically it's always increasing as you go to the right, or always decreasing. It doesn't change direction. If f is strictly monotonic on the entire domain, let's stop there for a second. The previous problem that I just did about checking whether these two functions are inverses both graphically and analytically. Well, I first graphed that parabola, right? It was decreasing from negative infinity to 0, where we found the vertex of the parabola, then it started to increase. So that was not a monotonic function. It was decreasing, and then there was a place where the graph changed direction and started increasing, or having a positive slope. So we had to restrict that domain from the vertex to just the part of the function in that particular case where it was increasing. Not that it always has to just be increasing, but it does need to be monotonic. So we restricted the domain of that parabola such that it was monotonic. Then it is one-to-one, and therefore has an inverse function. Now, as far as finding out or determining if a function is monotonic, we can type that function again into our calculator and do a visual inspection. But just to review and strengthen our calculus skills, for the example I do with you, you're going to help me with by practicing the problem yourself as well, we're going to check that monotonic situation by looking at the first derivative. Basically, kind of like doing a first derivative test. So steps for finding an inverse function, well, we need to check to see if it's one-to-one, visual or with your first derivative. We're going to swap the x and y variables again, as you saw me do with this linear function. We're going to resolve, after swapping the x and y variables, resolve it for y, and then label that as the inverse function, whether it's y to the negative 1 or f to the negative 1 of x, or we read that as the inverse of f of x, or the inverse of y. Determine the domain of the inverse function. Determining the domain of a function is much easier quite often than determining the range. So it says here we're going to determine the domain of the inverse function, which is the range of the original function. So we could take that original function, f of x, identify its domain, then find the inverse and find the domain of the inverse function, which is the range of the original function. Now, determining domain, your trig functions are a little bit more complicated with, maybe where the vertical asymptotes are of, say, for a tangent function, or maybe a little bit hidden, not really obvious from the equation unless you really know your unit circle and your trig functions, of course, which we should. But if you're looking at just a pure algebraic equation, we can be very cautious of restrictions in the domain if the independent variable, the domain, or generally the x variable is inside a even root or in the denominator of a rational function. Doesn't guarantee that there's a restriction, but like if it's in the denominator, but it very well probably will have. And then, of course, if you want to take it that one extra step, really make sure that your answer is are inverses of each other. You can check your definition of inverse functions here and make sure that these both expressions come out to be the value of x. We're not going to do this last step in our example of finding an inverse function, but we are going to do the other four. Maybe even, again, a bit more in depth than maybe you would. It'd be easier just to have the aid of a calculator, but we're going to practice our skills of derivatives as we go through this. So let's get to that example of finding an inverse function. Find the inverse function of f and state the domain and range of the original function f and its inverse the inverse of f. And our original function here is f of x is equal to 2x divided by the square root of x squared plus 5. Now, with the use of our graphing calculators, which is something we definitely need to practice, we can type this into our calculator, analyze the graph, and by analyzing the graph, determine the domain. And there's some horizontal asymptotes going on in here, so we'll have to recognize that asymptotic behavior, but we should be able to also identify the range. We should also be able to just look at the graph and determine if it is monotonic increasing or decreasing. In other words, is it 1 to 1 and thus has an inverse function. But, you know, that's fairly straightforward, hopefully, if you know how to use your graphing calculator. But I want to allow you the opportunity to, you know, remind yourself, re-strengthen your derivative skills and finding horizontal asymptotes of irrational functions. I'm going to step out. I'm going to reveal these solutions one step at a time, maybe pause the video. Find that first derivative, determine if it's monotonic increasing or decreasing based on the first derivative, and then, if you remember how to find those horizontal asymptotes, find the range of this function as well. We can again find the domain of the inverse function, which is a little bit easier, which will be the range of this original function, but I just want to review some skills with you as we go through the video. So just to quickly run through this, we have a domain. Now our denominator is in the, we have variables in the denominator. We can't divide by 0, nor can we take the even root of a negative number. So with the combination of those two, we set x plus 5 is greater than 0, we subtract both sides by negative 5, and we have x squared is greater than negative 5. Well, certainly anything that we raise to an even power is going to be positive, so it will automatically be greater than negative 5. So the solution is all real numbers. For testing whether the function is monotonic, thus being 1 to 1, we can find the first derivative here. I went through the quotient rule, the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, which required the chain rule. The 2 cancels out. We have a factor of x squared plus 5 to the 1/2 power and the negative 1/2 power, so that same factor is in both terms. So we take out that lowest power of negative 1/2. They both have a factor, both of these terms to the left and right of the minus sign have a factor of 2, so that 2 can get factored out as well. A little simplification, and we have f prime of x is equal to 10 over x squared plus 5 raised to the 3/2 power. So what's going on here is, again, our x has an even power. So whatever we put in for x becomes positive with the even power. Then we add by 5, keeping it positive, and thus, and we have a positive numerator. So this expression, take a positive and raise it to a positive, or an odd power comes out to be positive. The even root with no negative out front comes out to be positive. So the first derivative is going to be greater than 0, positive, everywhere within the domain, which is all real numbers, and thus it's monotonic increasing, and so thus it's 1 to 1, and we will have an inverse function. Now, coming over here, and maybe I'm going to point something out at the end of this that maybe would have saved us a tiny bit of time if we had thought of it at first, but horizontal asymptotes. This is an irrational function. I mean, there's a fraction bar, it's a fraction, but then it has a square root in it, so it's an irrational function. And so either way, though, we need to go through this limit process, and to find the limit as x approaches positive infinity, we multiply the numerator by 1 over x, and to get that into the even power or the square root, we take that x and we raise it to a second degree. So we have 1 over the square root of x squared, which simplifies to be x. So this is equivalently multiplying by 1. When we do that, we get ultimately a limit of 2. So as x approaches infinity, the graph is going to approach the value of 2. And to approach negative infinity, we need to have some kind of sign change to indicate that in our limit process. So we have, we can either do basically either negative 1 over x or 1 over negative square root of x squared as I've indicated, which is nice because then you just put a negative in front of your radical, and the limit as x approaches negative infinity is going to be -2. So we have, I didn't mark off, maybe I should have, the horizontal asymptotes. But if we were to have graphed the original function and try to find domain and range and whether the function is one-to-one with a graph, with a calculator, we would have indicated or seen this kind of graph. Now, just to again review a lot of concepts we've learned in the past, if I were to take this function and rotate it 180 degrees, it would appear to have symmetry about the origin. Well, that means it's an odd function, which and odd functions are you plug in opposite values of x and negative x and you get out opposite answers. Well, if I plug in opposite numbers in the denominator, the negative or the opposite will be canceled out by the even power, thus the denominator is always going to be the same, always going to be, well, the same whether you plug in a positive or negative x, but the numerator is just simply 2x. So yes, when you plug in opposite values into this function, when you plug in opposite x's, because that numerator, the sign of that numerator changing and the denominator not, you are going to get opposite answers, and thus this would pass the test for this being an odd function, which there now we can see whether you graph this with a table or more than likely with your graphing calculator. So we haven't found the inverse function yet, but we have done a lot of work of finding domain, finding whether it's one-to-one. This extra work of finding the range, this is me just again reviewing concepts. We could have found the inverse first and found the domain of the inverse, which would still give us the same values of between -2 and 2. Let's go ahead and find that inverse function now. Got everything cleaned up. Summary of what we just found here, domain, range, our sketch. We're going to take these x and y variables and swap places. So instead of y, we're going to have x is equal to 2y over the square root of y squared plus 5. And again, we want to now solve this for y. We're going to have to square both sides to get rid of this even root and manipulate the equation to the point where we can get y in terms of x, and that'll be the inverse function. Again, I'm going to step out and review the solution one step at a time. Got those xy's swapped, of course. That's how we started the problem. Squared both sides of the equation to get rid of the even power. We multiplied both sides by y squared plus 5, distributed the x squared to the parentheses. I moved my 4y squared over to the left with subtraction the same, moving the 5x squared to the right. When I got down to this point, I have y squared is equal to negative 5x squared over x squared minus 4. Well, if I go to get rid of this power of 2 by taking the square root of both sides, with that x squared being positive, that x squared term, whatever I plug in for x, is going to be positive because of the even power, then I get multiplied by negative 5. Now I can't square a negative number. So in this format, the numerator is guaranteed to be negative, and thus I can't take the square root of it. So I multiply the numerator and denominator by -1 to get rid of that negative that's in the numerator. And also, of course, that's going to take the binomial in the denominator and swap places. Negative x, or x squared times -1 is negative x squared, and -4 times -1 is positive 4. Now, this expression has a pretty tight restricted domain for where, you know, it can be positive, but it's not guaranteed to be negative like we had in the numerator. So I go ahead and I then take the square root of both sides and identify it as the inverse of y. I get plus or minus the square root of 5x over the square root of 4 minus x squared. Now again, you can't take an even root, excuse me, of a negative number, and you can't divide by 0. So 4 minus x squared needs to be greater than 0. We get it solved for x squared. We square root both sides. And with inequalities, you need to change the direction of the sign for the negative answer. And so we have that negative 2 is less than x, which is less than 2, which, right, the domain, I just solved for the domain of the inverse function, and it's checking out to be the same as our range of the original function. So that's all checking out to be good. We need to deal with this plus or minus that we have. I didn't pick a real simple question for finding an inverse. We have a plus or minus here. Well, it's not both, okay? We're looking for the function which is the reflection over the line y equals x, which is something like this. This is only a quick sketch. I'm not sure if this really crosses or not, but we're looking for the reflection of this original function f of x over the line y equals x. And if you use your graphing calculator to graph both the positive and negative version of this answer, one of those answers, which is the negative one, will come down and cross through the origin this way. Still have a vertical asymptote of negative 2 and positive 2, but it would be coming through like this, which is not your reflection over the line y equals x. We're looking for a graph that looks like this. And the graph that is that reflection over the line y equals x is the positive version of our answer. So our inverse function is the square root of 5x over the square root of 4 minus x squared. And you can check that if you would like with the definition of inverse functions, but I have a graphical check right here, so we're going to leave it at that. We're going to move on to the derivative of an inverse function, write out that theorem, if you will, and some formulas so that we can get to our last two examples and find my remote. Let's talk about a few properties of the derivative of an inverse function. If f is a function whose domain is an interval I, then if f has an inverse function, then the following statements are true. If f is continuous on its domain, then the inverse of f is continuous on its domain, which is the range of the original function. If f is increasing, which means its first derivative is going to be positive on its domain, then the inverse of f is going to be increasing on its domain, so its first derivative is going to be positive. If f is decreasing on its domain, then the inverse function is decreasing on its domain. And finally, if f is differentiable on an interval containing c, and if f prime of c is not equal to 0, so basically, the slope of that original function, as long as it's not equal to 0, because when you reflect that over the line y equals x, that horizontal tangent line is going to become vertical, which would be an issue with trying to find the derivative. So that f prime of, or that derivative of f of c cannot equal 0. Well then, the inverse function, or the inverse of f, is differentiable at f of c. Now again, that domain and range is swapping, right, as you find inverses. So f is differentiable at c, and the inverse is differentiable at f of c. F of c is the y value of your original function, but when you take the inverse, and when you start talking about inverse functions, the y of the original function is the x of the inverse function. So that's why you see that f of c there. Okay, so let's look at a rule, the derivative of an inverse function, this formula that allows you to sort of do this a little bit more quickly than actually having to find the inverse and then having to find the first derivative to find this answer. You'll see it in the formula. This is what the whole video is building up to, the derivative of an inverse function. Let f be a function that is differentiable on an interval I. If f has an inverse function which we're going to identify as g, then g is differentiable at any x for which the derivative of f, or f prime of g of x, is not equal to 0. And this is how the formula is initially given in the book that I teach out of in class, or will be teaching out of in class. It says, the derivative of g of x is equal to 1 divided by the derivative of f, or f prime of g of x. Okay. I find that initially to be kind of confusing, so I'm going to go ahead and take this and just write it in terms of like the inverse function notation. The derivative of the inverse of f of x is equal to 1 over the derivative of f of the inverse of f of x. And even that's kind of confusing. So let's see here. Derivative is slope. So the slope of the inverse function at its x is equal to 1 divided by the slope, the derivative, the slope of the original function, and we're plugging in f, the inverse is f of f, the inverse of f of x, easy for me to say. Basically the y that we get from the inverse function. Well, why are we asking for y? Well, the x of the inverse function is the y of the original function. Remember we talked about that domain and range swapping places as we find inverses. So the y of the inverse function is actually the x of the original function. So let's go back to that original diagram that I started with this video, those two linear functions, which slopes don't change, but just for simplicity's sake. We had y equals 2x plus 4. The slope of the original function was 2. We swapped the x and the y, we resolved for y, and we got the inverse of y was equal to 1/2 x plus 2. Well, yeah, these slopes are reciprocals of each other. These slopes are reciprocals of each other. And this formula says that the slope of your inverse function at its x is equal to the reciprocal 1 over the slope of the original function, but you're plugging in the y, again, of that language of the inverse, or the y of the inverse, which was 2, was the x of the original function. So the slope of the inverse function, the slope of the inverse function is equal to, at its x, is equal to the reciprocal of the original function at that inverse's y value. Well, that y value was the x of the original function. And so right here again, 1 over f prime, or the slope of the original function, where you're plugging in the y of the inverse function, which was the x of the original function. Now I'm going to really hit on this hard and kind of actually do the first example longer than I need to, just to show you that swapping of the domain and range and how those slopes are inverses of each other. And then we'll do the last example, very streamlined, allowing this formula to basically just really shortcut the process to help us find derivatives at particular x values of the inverse function. Verify that f has an inverse. We're going to assume we're talking about functions like we have all video. Then use the function f and the given real number a to find the derivative of the inverse of f of a. Okay, so normally I just tell my students, if you really get stuck on how to do a problem, just let the formula tell you what you need. Okay, first thing it says is, verify that f has a function. Okay, it needs to be monotonic. So we're going to find the first derivative. So f prime of x is equal to, that's a constant, so it's 0, and negative 3 times 3 is negative 9 x squared. So no matter what x is, it's going to become squared, and therefore this factor will be positive times negative 9 will be negative. So the first derivative is always going to be less than 0. So this is monotonic decreasing. A is equal to 5, so f, the inverse of f, the derivative of a, is equal to 1 divided by, well, I need the derivative, and, well, actually I just figured that out, right? It's negative 9 something squared. And then if you didn't really catch what I was trying to point out to you in the previous screen, then you might be going, okay, well I need the inverse of f of a. Okay, so maybe we'll burn some calories and do that. And if I want the inverse function, I'm going to take the x and the y and swap them. So let's do this in orange. So we have x. This is the extra part actually that you don't really have to do. I'm just trying to tie everything together, and then we'll streamline the last example. So this y is going to become x. We're going to put a y here. We're going to resolve this for y. So we're going to subtract both sides by 2. divide by negative 3. I'm going to turn this around too. And then we're going to take, the cube root of both sides. And now that I've finished resolving for y, this is my inverse function. I'm not going to check it with the composition things, the f of g and the g of f, but this is my inverse function. So now that I know what the inverse of y is, I can come up here and go, okay, well I was looking for the inverse, and that's this cube root. Of x, which I'm plugging in a, so it's going to be 5. Oh. Minus 2 over negative 3 squared. And this is going to come out to 1 over negative 9 times 5 minus 2 is equal to 3, and 3 divided by negative 3 is negative 1, squared, and the cube root of negative 1 is negative 1. Negative 1 squared is positive 1, and positive 1 times 9 is negative 1/9. The derivative, or the slope, of my inverse function at a is equal to negative 1/9. Now, what I want to point out here, and to show what I was trying to point out in the previous screen, I took the time, like I said, to find the inverse function, and then find it, the value of that inverse function at a, which came out to be negative 1, and then we plugged that into the first derivative. Okay, I didn't actually have to find the inverse function. There'll probably be problems in your homework where you really will have a very difficult time finding that inverse function. So we can streamline that if we remember that, okay, the a again was effectively, see it going into the inverse function and us getting a y value. Well, that a is the domain of the inverse function, it's the range of the original function. So I can say, okay, well, I'm recognizing now that this 5 is actually the y value for the original function. So if I take this original function, and let me get this out of the way here, and say, okay, well 5, let's do it in purple, 5 is equal to 2 minus 3x cubed. Subtract both sides by 2. Divide both sides by negative 3. And get negative 1 is equal to x cubed. And then cube root both sides. And get negative 1 is equal to x. The x that is there from my original function becomes the y of my inverse function. Look what I have inside for this value of the inverse of f of a. We got negative 1. So I don't have to find the inverse function to find the slope of the inverse function at a. I just have to recognize that this swap of the domain and range is going on, and saying, okay, the x for the inverse function is actually the y of the original function, and I can find that value, that inverse of f of a lot easier, and then I can just plug in the negative 1 right here. Actually, I think I pointed to that line. I should have been pointing to this one. Plug in my negative 1 here and get my answer a lot quicker. So let's streamline that as our final and last example of the video. As our last example, f of x is equal to x plus 4 over x minus 3 with restricted domain where x is greater than 3. We have an a value of 8, so we are going to find the slope of the inverse function at the value of 8. To streamline this again, we are going to find the derivative of f of x to verify that it's 1 to 1, and thus the inverse function exists, plus we need it as a denominator down here. And we're going to set f of x equal to a, solve it for x, which is the y value of that inverse function. Go ahead and plug it in, get our answer, and we'll be done much quicker than the last example. So f prime of x is equal to denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over that denominator squared. And so when we get done cleaning all this up, this is multiplying by 1, so that's not really going to do anything. Distribute that -1, and we have f prime of x is equal to x minus x, which is 0, -3 minus 4, which is -7, over x minus 3 squared. Now, the denominator is always going to be positive with that even power. The numerator is negative, so our first derivative is going to be less than 0 always, so this is monotonic decreasing, thus it's 1 to 1. Okay, we need to find this this y value here, the inverse of f of a. So we're going to let this function equal 8. So 8 is equal to x plus 4 over x minus 3. Multiply both sides by x minus 3, and we get 8. X minus 24 after we distribute, which is equal to x plus 4. Move this x over to the left, and we get 7x. Add both sides by 24, and we get 28. Divide both sides by 7, and we get x is equal to 4. So the slope of the inverse function at 8 is equal to 1 over, f prime, the slope of the original function. Well, that's -7 over, parentheses, something minus 3 squared. And again, the y of our inverse function, the inverse f of a, is the x of our original function here, which we found to be 4. So it's going to be 4 minus 3 squared. Well, 4 minus 3 is 1, and 1 squared is 1, and -7 over 1 is just -7. So our final answer is -1 over 7. So started summarizing the numbers and had a little interruption. So what we have here is that the slope of the original function at 4 was -7. So swapping that domain and range, the slope of our inverse function at 8 is the reciprocal of -1/7. So I'm Mr. Tarou. Go do your homework. Let me find my remote.